Up to the last lecture, we have studied different points about linear time invariant systems. We concluded with determining from the impulse response properties such as causality, stability, memory, etc. of a linear time invariant system. At this point, we have to take a digression and study differential equations for a while. Since I do not expect every student of this course to have a background in differential equations, all I intend to do here is to present the necessary part of differential equations, the part of differential equations that is necessary to proceed with my business, no more. So, we will study differential equations for a while, then we will see the relationship, we will examine the relationship between differential equations on the one hand and linear time invariant systems, which are our main object of study in this course. So, differential equations. A differential equation is an equation that relates two functions. In our context, they will relate two functions of time. One function xt will be called the forcing function, also sometimes called the excitation, and from the signal system's point of view we will call it the input. Different names for the same thing. The other function that is involved in a differential equation is what we will designate by yt, cut. The other function that we will concern with in a differential equation we shall designate by yt and give it names such as the solution, the response, or from a signal system's point of view the output. How are these two functions related in a differential equation? On the right side conventionally of the differential equation will appear simply xt, the forcing function. On the left side we will have a certain combination of the various derivatives of yt. So, if we denote the kth derivative of yt by dkyt by dt to the k, then what is going to happen in the construction of a general differential equation is that some n of these derivatives of yt will be combined together to form a function which is equated to xt in the following manner. We first need all the n derivatives of yt, the first n derivatives of yt in a set. So, we shall make a set like this, k equals 0, 1 to n, we construct some function, some combination of these entities dk yt by dtk. This function I will simply call f for the time being. This is the left side of the equation, and on the right side, as I said, we just have xt. This makes a general differential equation. Let us make a few examples. Let us say Here is a general example. We have the second derivative and the first derivative of y t, d y t by dt and d squared y t by dt squared, and we of course have y t itself, which is considered to be the 0th derivative. Hence, k equal to 0 is also mentioned in the set of derivatives of y t that we will relate to x t, the equation. So, this is one particular example of a differential equation involving y t in the context of x t with the forcing function equal to x t. So, this is rather a complicated equation that we considered, but a typical example. There are, let us just make one more example. Here we have just the first derivative and the 0th derivative y t. Y t also is multiplied by a function of time. So, these are examples of a general differential equation, and our interest in differential equations is to solve them. So, what does it mean to solve a differential equation? To solve a differential equation is to find a time function y t which, when substituted in the left side of the equation will result or will compute to x t at each t of interest. So, at every instant of time, if you substitute y t into the left hand side and compute the function, then that function should evaluate to the value of x t. Then you say that y t is a solution for the differential equation. Now, there are many surprises and secrets with differential equations. Even the simple differential equations that we will be dealing with, certainly not of the kind of the two examples I have just provided, even those will turn out to have lots of solutions, unfortunately not just a single solution. So, uniqueness of the solution of a differential equation will concern us for a while, and we will have to ensure that in order for a differential equation to represent a system, we have to make sure that the number of solutions we have are somehow sifted through to obtain a unique solution. So, now that we know what is the solution of a differential equation, let us move on and concern ourselves with our immediate problem. The immediate problem is to find representations for linear time invariant systems in terms of differential equations. As long as we confine our interest to differential equations only to representing LTI systems, it turns out that we can keep away from concerning with most differential equations except those of a certain narrow kind. This narrow class of differential equations which can be used to represent LTI systems are linear constant coefficient ordinary differential equations. This class, which is linear, has constant coefficients and is ordinary, is the only class of differential equations that we need to concern ourselves with. For the rest of the lecture and for all of the future, when I mean a differential equation, I will simply mean a linear constant coefficient ordinary differential equation, simply abbreviated to DE. What is the general form of this kind of a differential equation, this particular kind of a differential equation? The general form we will express just as we did for the general differential equation, putting x t on the right hand side, but on the left hand side the general form we wrote earlier will be replaced by a very particular kind of form, and that is so this is the most general form of a linear constant coefficient differential equation, and this is all the kind of differential equations that we will bother with. Okay. Now, we have to understand how to solve such an equation. We are not concerned with solving other more difficult forms of differential equations, only this kind, and in the process of understanding how this is solved, we will unravel several mysteries of the differential equation. Before we begin, let us understand a few very useful properties that this linear constant coefficient ordinary differential equation possesses, which other differential equations generally do not possess. Let me enumerate them one by one. The first is linearity. Suppose y t is a solution for the equation when x t is the forcing function. Using the other terminology that we just suggested, if x t is the input, suppose y t is the output of the differential equation. Then for this kind of a differential equation, under certain conditions, only under certain conditions, it will turn out that if two inputs are superimposed, x 1 t and x 2 t, whose respective outputs are y 1 t plus and y 2 t, then the response to x 1 t plus x 2 t will be y 1 t plus y 2 t under certain conditions. More importantly, these differential equations have a very interesting property, and that is that if you time shift the input, the output will also get time shifted. If x t goes to y t, then by what we can call the time invariance property, if you apply x t minus t naught, then you will have a solution in y t minus t naught. But these things are best understood first in the case of the simple derivative. Suppose the differential equation is simply dy t by dt equals x t. this represents a system in some way, and this system is clearly linear and time invariant, because if you scale x t and when y t is the solution, then the correspondingly scaled version of y t will also be a solution. It also supports superposition, it also supports time invariance. If I time shift x t, so that I apply x t minus t naught as the forcing function, then correspondingly y t minus t naught will be the solution. Okay. Now, what we want to do is to go into understanding the solution of the differential equation itself. Now, the differential equation has a solution, right. Now, the solution depends in general on two things. Studying the solution of the differential equation, depends first, it depends on the forcing function. If x t is changed, it is natural to expect that y t will be changed. That is to say, for different the outputs are different. For different inputs, the outputs are different. Only natural, one would think. But there is another thing on which the output depends. The form of the differential equation, that is, how many terms, how many derivatives of x t. This is in fact called the order of the equation. And the coefficients. These two things together, the values of the coefficients a k and the order of the equation completely determine the form of the equation. The point we are making here is simply this, that if, well, we said in the first point that if the input changes, then the solution will change. In the second point we have made here, we are saying that even if the input is unchanged, if the form of the differential equation changes, that is to say, either the order changes, or even if the order does not change, if any of the coefficients changes, then the solution will change. Thus, the solution depends both on the form of the equation and the form of the forcing function, the particular case of the forcing function. Now, it turns out that in order to get information about the solution that depends only on the form of the equation, we have to solve something called the homogeneous equation. Let me say that again. I am saying that aspect of the solution that depends only on the form of the differential equation is understood by solving the homogeneous equation. What is the homogeneous equation? The homogeneous equation resembles the original differential equation, except that the right hand side where we have the forcing function we replace with 0, the identically 0 function of time 0. So, the homogeneous equation is simply this is the homogeneous equation. Clearly, this equation and whatever we learn about its solution cannot depend upon the input, because there is no input. Irrespective of what input we had applied in the original equation, we have stripped the input in this equation. So, irrespective of what input is applied, there are certain things about the solution that will depend upon the form of the equation alone, that is on the left hand part of the equation alone, and that is what we want to learn by solving first this equation. So, solving the homogeneous equation, HE for short. Now, what can we say about solving the homogeneous equation? How do we look for a solution? On the right side we have 0. We somehow want to find a yt such that when you evaluate the different derivatives of yt, scale them by the respective scale factors a k and add them all up, they add up identically to 0. How do we go about this? In order to see how we go about this, we shall invoke one of the most powerful functions in mathematics, the exponential function. So, in order to understand how we solve the homogeneous equation, we have to recall some facts about the complex exponential function, the general exponential function. We will recall from our earlier mention of the complex exponential that it is of the form e to the power st, where s is generally a complex number. Now, why is the complex exponential of interest here? What business does it have with differential equations? Very, very simple. This is the only function which possesses the following property, that when it is differentiated, it maintains its form. The result of differentiating an exponential function, a general exponential function of this form, is still the same function scaled by a certain complex number, no other change. Thus, if you take the time derivative of this, all you get is s e to the power st. Since s is a certain constant which is the parameter of the exponential, we see that the result of differentiation is still a function of the same form. This fact about the exponential is going to be crucial for understanding how it plays such an important role in solving the homogeneous equation. Right now, we will take a jump which is arguably without justification, and say that the solution for this differential equation is indeed a certain complex exponential e to the st, without yet knowing what that s is. So, we do not know what the s is, but we shall assume that the dE, the homogeneous dE, is solved, that is, has a solution of the form e to the st. Supposing it has, then let us see what happens. If it is a solution for this differential equation, then if I substitute e to the st for yt and evaluate the left hand side, I should get the right hand side, which is 0. So, let us substitute it and evaluate it. Evaluate the left hand side. left hand side is this, we have written it several times over. This, and if we evaluate this, what we get is a k times the kth derivative of e to the s t is s to the k e to the s t, because every time you differentiate it once, s, one more s comes out of the exponent and lands on the ground. So, we have a to the k, a k times s to the k e to the s t. So, you see that all the derivatives are gone now. We have already carried out the differentiation. We have this, and since this whole thing was taken out of the left hand side of the homogeneous equation, we know that this entire expression, this sum of capital N plus 1 terms must be equal to 0. Now, let us look at this carefully. We have e to the s t unindexed by k as one factor in every term of this expression. There are n plus 1 terms, each term is of the form a k times s to the k e to the s t. E to the s t is a common factor in all these terms and it has no index of k. So, it can be taken out of the summation and we can write this as e to the s t summation k equals 0 to n a k s to the k, this equals 0. Now, let us look at this carefully. This part, the second of the two factors, is a polynomial in S k, in polynomial in S. And this is a time function. So, e to the s t is a function of time and that is getting multiplied by a polynomial in S, and this product of this polynomial times the time function e to the s t is identically 0. Identically 0, I mean, by identically 0 I mean that it is 0 for every point of time. Now, if this thing has to be identically 0, if it has to be 0 for every point of time, then let us see which of the two factors can be responsible for it. Clearly, when we have an expression that is a product of factors, then the product can be 0 only if one or more of the factors is 0. So, let us try to fix the blame on these factors and see which of them could have made the entire product 0. So, can e to the s t be 0 for all t? Well, from what you should have already learnt, from what we already covered in this course a few lectures ago, where we went into considerable detail about the form of the exponential function for various cases. S was a real number, S was a positive real number, S was a negative real number, S was a purely imaginary number, S was a complex number. For all these cases, we found one very common and very steady fact about the complex exponential, about the general exponential, that e to the st is not just not 0 at all time, it is not even 0 at a single point of time on the time axis. In short, we know that e to the st is never 0 for any finite value of t, e to the st is never 0. Now, why is this important for us? It is important for us because, going back to our solution of the homogeneous equation, we are trying to find a solution to the homogeneous equation, and we had two factors, the time function and the polynomial in S. We were trying to see which of these could be responsible for the entire expression evaluating to 0. And this latest remark that we have put down clearly shows that if this product has to go to 0, then e to the st is not going to contribute in any manner. E to the st is not going to help you to make this product of factors go to 0. Hence, in order to solve the homogeneous equation, in order for the left hand side of this expression to evaluate to 0, the burden falls on the polynomial in S. Only this can be 0. So, when can it be 0 is the next question. In order to ask when can this polynomial be 0, let us just look at the polynomial. It is an algebraic polynomial. This is just an algebraic equation, and it is a polynomial equation of order n. Of degree n, sorry. So, let us dig out some of our results that we all know from high school about solving a polynomial algebraic equation. We know that this polynomial algebraic equation will have n roots. Because it is of degree n, it will have n roots. And what are roots? Roots are values of s at which the polynomial goes to 0. Right. So, since there are n roots, let us name them S1 to Sn. These are the n specific numbers, not necessarily real numbers, they could be complex numbers, which if you substituted in this polynomial equation in place of s and evaluated the left side, it would evaluate to 0. Now, what is different from this homogeneous algebraic equation and the earlier homogeneous differential equation? We seem to be saying the same things about a very similar equation now. We had a homogeneous algebraic differential equation. We got rid of the derivatives somehow by assuming that the solution was an exponential, a general exponential, and we have now brought it to a homogeneous algebraic equation. This has helped us in a very, very unique manner. Earlier, our homogeneous equation was an equation that related two functions of time. On the left side of the differential equation, we had functions of time, yt, dyt by dt, and so on. On the right side, we had 0 of t. So, it was really not one equation over there. The homogeneous differential equation is an infinite collection of equations, one for each instant of time. All of them have the same form, and that is why we can write it in one single expression. But theoretically, or if you look at it carefully enough, you recognize that one differential equation is actually an infinite collection of equations applying for each instant of time. Here on the other hand, this polynomial equation, which is also homogeneous because the right hand side is 0, is an equation between numbers. It is only about numbers, there is no time index anymore. We just have to solve this once, whereas conceptually, to solve the differential equation you have to solve it every time. For every instant of time you have to solve it separately. Here you have to do it only once. So, that is the difference. We now have to look at how these roots are to be used to demonstrate that they are solutions for this algebraic homogeneous equation. By saying that the roots are S1 to Sn, what we essentially mean is this. We mean, for example, that k equal to 0 summation to n a k S1 k S1 to the k is 0 and so on for S2 and other roots until it is also true that k equals 0 to n a k S n to the k equals 0. So, every one of these is a root for the algebraic homogeneous equation. That is fine. The matter of solving the algebraic homogeneous equation ends here, but this was not our original problem. The original problem is to solve the differential equation, the general non-homogeneous differential equation containing the forcing function x t. From there, we digressed to solving the homogeneous differential equation, and from there we have further digressed to solving the homogeneous algebraic equation. Now, let us start walking backwards and retracing our steps. Beautiful. सही टाइम पर आपने कट किया, कोई वो